Thank you, Konstantin, and thank you everyone for joining. So I will introduce a bit to the subject. So today we have a very interesting presentation regarding the analysis of unconventional field, and it's based on Montney field, as you can see. It's one of the biggest fields in gas fields in Canada, but the idea of this analysis is that we can perform the well performance evaluation based on a very limited amount of data, even sometimes only public data, which is the case of Montney field. And it's especially interesting for our European community because it's based on the physical approach. So it's applied not only to the Canada or to the North America, but it's applied to any tight gas field in the world. And then let me introduce Viacheslav. So Viacheslav is our speaker today, who has more than 20 years of professional experience. He is a petroleum and reservoir engineer and a consultant who helps operators to increase production and recovery. And his area of expertise includes well performance analysis, artificial lift, hydraulic fracturing, water flooding, and you can see he has a lot of experience in different parts of the world. And I think that's it for the brief introduction. So I pass the ball to Viacheslav.
Thank you very much, Boris and Konstantin. Before we go into the presentation itself about the subject, I want to tell a little bit of a background, why I did the study I'm going to present today, why it was interesting to me. I started my professional experience work in organization that was very performance oriented. That was 20 years ago. And in that organization, for every well, production potential was calculated routinely on the monthly basis, and performance gap calculated, and actions developed to reach as close to potential as possible. And that was done, that was institutionalized, and on all the levels from the production shops up until to the executives in the organization. The same applied to hydraulic fracture. Hydraulic fracture design was done according to the unified fracture design approach introduced by Professor Economides and Professor Valko. And for me, that was a reality for several years. And those were reservoirs with a relatively low permeability, 1 millidarcy range, 10 millidarcy range. Then after that, when I started to work as a consultant and work in different parts of the world with different operators, I realized what was the reality for me in the beginning of my career in the early years. People don't necessarily adhere to the same approach. They do not necessarily know their production potential. And partially that may be because they got lucky with the reservoirs. The reservoirs are not so tight. They may be 100 millidarcy or darcy range. And of course, when someone gets lucky, there is a less need to go and excel in performance. But that was a revelation for me that not all the companies are calculating production potential and trying to close performance gap on a routine basis. Then speaking about North America and the recent 20 years when hydraulic fracturing, massive hydraulic fracturing, even ever with a bigger size in every year, was became the factory-like approach, and all the companies are doing more or less the same. And when you speak to people, you ask about hydraulic fracture design, they tell you that it's very easy, we just pump X tons per meter. Or when you ask about reservoir engineering, they say it's not that interesting as conventionals because there is not as many things you can do. And that all sparked my interest to look at the public data which is available in North America and see, is there really any difference in well performance between operators of a specific formation and between the areas of a specific formation. And this is why I did the study. In this presentation, I will talk about the study. We'll talk about first what production potential is. We'll talk about the Montney Formation, which is the subject for this analysis. Well performance analysis, talk about data that were analyzed, see examples, discuss results, and conclude. Speaking about production potential, you can see illustration here on the right. And we have gas rate versus time, and actual historical gas rate are these red dots. But the production potential is this curve that would have been attained if the well had produced the maximum it could. And always the actual rate, whether it's oil or gas, it is lower than potential due to suboptimal design, suboptimal operations, and various types of restrictions. That gap differs by operator, and it can help distinguish between less efficient and more efficient operators. Calculating and closing performance gap should be a routine process similar to the organization I worked in the beginning of my career. The question for this study is, can we estimate performance from public data, and how can operators close their performance gaps? We will be talking about Montney Formation, which schematically you can see where it is located in Canada, between the provinces of British Columbia and Alberta. This is a siltstone formation of Triassic age. Thickness is up to 300 meters, and permeability is in the order of 100 nanodarcies. It may be higher, may be lower, but this is the approximate order of magnitude. And of course, such reservoir is developed with multi-fractured horizontal wells. In the bottom, we can see historical production just of the British Columbia side of the Montney, which is the subject for this analysis. Gas rate currently is about 200 million cubic meters. There is oil or condensate depending on the well. And there is about 6,000 active wells. And also we can see that water is growing. Please note the log scale on the y-axis. To analyze such wells with multiple hydraulic fractures, horizontal wells with multiple hydraulic fractures, the approach is very well established, and it has been around since 2010 or maybe earlier. This paper is a good paper to see about how production data from multi-fractured horizontal wells should be analyzed. And I will not be going in all the details of the slide, but the approach is to take production data, pressure data, calculate derivatives, make log-log diagnostic plots, then specialized plots based on the flow regime, which very often it is linear, and then go with the model and conclude with the model. This is what's supposed to be done with proprietary data. And this is what operators are actually doing using ray tracing analysis software. But for public data, we cannot exercise this approach because public data generally do not have flowing pressures. We don't have that information, but we have another useful information that in 100 nanodarcy rock with a well with multiple fractures, the early flow is linear. So we don't need to identify flow regimes. We know that this linear type plot, square root type plot, is our plot of interest. And if we talk about how a well performs during that specific linear flow regime, the equation is as following, where gas rate is inversely proportional to square root time if a well produces at a constant flowing pressure. And there are some reservoir parameters, square root of permeability, the total fracture area of all the fractures, and the drawdown. Details of this equation can be found in these SPE papers. And the earlier paper by Wattenberger dated 1998. If we look closer at this equation, we can see that there are some parameters that we need to know and we don't affect, like formation permeability is given. And these reservoir properties and fluid properties are given. On contrary, there are some parameters like total area, which we can optimize for a given propant mass. And now I'm talking about the unified fracture design approach. And the drawdown needs to be maximized to get the maximum rate. This is manageable part versus the non-manageable part, which is highlighted in gray. And for the purpose of this study, I call the whole proportionality coefficient a well performance factor. And as a part of well performance factor, we have square root of k times a, which is usually called linear flow parameter in the rate transient analysis applications. And also there is a drawdown. This well performance factor may be determined from public data because we can simply plot rate versus 1 over square root time or reciprocal rate versus square root time and get the slope. If we have proprietary data, then our goal is to determine all the constituents of this performance factor, like formation permeability and drawdown itself. Now, looking at how the actual data behaves in these coordinates, reciprocal rate versus square root of time, we should first talk about the true production potential. This true well production potential is not known from public data. It exists if we run a well on the lowest bottom hole pressure technically possible, then all the dots will align to this dashed line. This doesn't happen for various reasons. And the first period of well performance, we can see the dots are significantly deviated from this dashed line. And this period 1 is when a well starts production. Usually it is choked. Usually the flow rate is high for the tubing installed and there is a significant frictional component in the wellbore. Therefore, there is a significant deviation between the actual production and this line. But again, we don't know this line. Period number 2, the dots align on the straight line. This is when the well is not choked significantly anymore. The rate is lower, so there is no significant frictional component. And the well here produces the closest to potential. It may be actually very close to its potential. And then later deviation happens, which may be for reservoir or non-reservoir related reasons. Reservoir related reasons are, for example, when the true flow regime information changes from linear to transitional. And the example of non-reservoir related reasons is liquid loading. The analysis I performed is to determine this tangent slope, which is the closest to well production potential. For every well, I plot reciprocal rate versus square root time and determine this tangent slope, which characterizes well performance. I applied to about 6,500 wells with production history in the British Columbia part of Montney. Historical production is taken as and up to June 2024, and the operators listed in here are also as of June 2024. Some changes have happened since then, some M&As happened, but this does not affect the outcome of this study because we are not talking about specific operators, rather we are talking about the approaches operators took or may take to perform better. Together with production data, I analyzed well information. There were deviation surveys available, well tops, hydraulic fracturing data, and completion files. And in many cases, when looking at the slopes in the coordinates we just talked about and seeing some changes, I went back to completion files to understand what was going on with the well. And that was very interesting to do because you see a change and then in the completion file you see that velocity screen was installed or well went to plunger lift or there was a frac hit. Consulting these completion files was very useful to understand what was going on with the wells. Here we'll be talking about 10 operators, which for the purpose of this study I call major operators. They have more than 100 wells or had more than 100 wells with production history at that time. And I will not be naming operators in the results except for a couple of examples, but rather calling them A, B, C, D, E, F, G. Again, because it doesn't matter what the name of operator is. What matters is the approach. Among 6,500 records, about 4,500 records had also tabulated fracturing data. And this helped us to normalize performance by proppant mass. Before we go and look at the results overall, let us look at some examples. For each of the example, we see on the top gas rate versus time, and on the bottom reciprocal rate versus square root time, the linear type plot. For example 1, we see a long linear flow, and here we can see dots and calculated potential, estimated potential. We see that the flow is linear or apparently linear for 12 years. And we can see that, or we can say that probably this was a very efficient production with no deviation from linear flow. In example 2, we can see that after a certain time, after 2.5 years probably, the rate started to deviate from this modeled curve. And on the reciprocal rate, we see an inflection. Such types of behavior indicate operational things. And in this case, that was possibly a liquid loading. This is a non-reservoir effect. Reservoir doesn't behave with inflection like this. In example 3, again, we see an inflection here, but then the data returned back to the original slope. And what happened here is probably liquid loading again. But here, according to the files, plunger lift was installed. And in example 4, we see that after some time, rate dropped and aligned with a different line and with a different slope. That was because coil tubing velocity screen was installed to prevent liquid loading. And as we can see from these 4 examples, operational practices matter and affect production. This is another example. It's an oil well And one of the more recent wells from, I believe, 2020s already. On the left plot, we can see flow rate of gas and oil versus time in a log-log scale. And this is kind of a decline curve type of analysis when we plot rate time. And if you look at the slope, in the beginning, we see several points that align to the expected slope of minus 0.5. However, shortly after, which we can see about less than a year, slope changed to minus 1. And if I didn't know the environment, I would say, okay, that may be a depletion. Slope minus 1 is a possible sign of a boundary dominated flow and depletion. However, because I did not do this analysis in a vacuum, I know that this cannot be the case. 100 nanodarcy, we cannot see depletion in 1 year. And then when you estimate flow and bottom hole pressure, we can see that the rate was very low for such a diameter of flow, which was a casing, 4-inch casing. And what was happening is probably flow was inefficient, and we are in the hook portion of the VLP curve. So flow and bottom hole pressure was increasing. And now, again, we're talking about non-reservoir effect. And here are some consequences. First, if you're doing decline curve analysis and not doing any physics, not incorporating physics, the results may be wrong. And they can be wrong both ways. They can be too conservative or they can be too optimistic. And because they are affected by current operation practices. Second is if we are talking about the value of an organization, the value of an operator, if the well is operated like this, the full value is not obtained, not exercised. However, if I'm looking at this well from the perspective of acquisition, for example, and I see the unrealized potential, and I know that here is the production potential, and there is a possibly higher hidden value in this well or wells of this operator. Now let's talk about the results of the analysis of 6,000 wells. Again, we are looking at performance factor, which is proportional to square root permeability, area, and drawdown. Here we can see the calculated performance factor for about 6,000 wells. And note please the log scale on the y-axis, where performance factor increased significantly more than order of magnitude throughout this time. Here on the bottom left plot, we can see total proppant mass per well versus the first production date. And we can see again increase. That was ever increasing proppant mass with time. What we really are interested in is to look on a normalized basis when we divide this by this. And why we are interested? Because we are interested in fracture area over proppant mass. We spend proppant mass to get fracture area. If we do this efficiently, this ratio is high. If we do this not that efficiently, this ratio is lower. So when we divide this by this, we get this plot in the bottom right corner. We call it normalized performance factor. And now we can see it doesn't really change much from 2013 to 2024. It stays in the same range between about 0.1 and maybe 2, about an order of magnitude difference. Next, when we are doing this normalized performance factor, that was interesting to me what it is related to, what affects it. And after certain thoughts and considerations and different things, tried different things, I noticed that normalized performance factor by well correlates with water-gas ratio. We can see for the higher water-gas ratio, we don't really have high normalized performance factor. The higher water-gas ratio, the lower performance is. And this observation is in line with the observations from this paper dated 2013 by Dr. Wood, where he talks about water distribution in Montney. And according to that paper, in the upper portion of the Montney, there are areas with a higher water saturation due to inefficient charge and inefficient water displacement due to heterogeneity. And now it's interesting to see, okay, these higher water-gas ratio, lower performance, what affects it and how it changes areally, how it changes from operator to operator. For example, can this be preventable, for example, completing in different interval, or it was inevitable, lower performance, higher water-gas ratio? We will first compare several operators using different plots. First, performance factor versus propant mass on the top, and then our plot of normalized performance factor versus liquid gas ratio. Here, for example, for shell operator, we can see, compared to all the data, which is in gray, we can see that shell data for a given propant mass, there is a higher performance factor. The shell data goes right through the upper portion of the data, which may suggest that shell is doing better job in completing and fracturing and getting a better result. This can also be seen from this plot, where this green line illustrates approximately the middle of this cloud, and the shell data are consistently above for every given liquid gas ratio. The shell data are above this middle line. Ovintiv is the big operator here in Montney, and we can see there is a cloud of performance versus propant mass, but again, the data is in the upper portion, regardless of the liquid gas ratio, the data is always above. The same applies to this operator. And now we'll look at three other operators. Operator G, the data is mostly below the average curve. And for example, operator D, we can see consistently higher liquid gas ratio, lower performance, and the data is somewhat below the average green line. Therefore, we see the difference in performance between 6 operators. Now, to do a corrected normalized performance factor to take into account the water gas ratio or liquid gas ratio, we want to, for every point, we want to calculate the corresponding corrected effective performance. What if this well, for example, did not have that high water gas ratio? What would be the corresponding corrected performance? And simply we go along these gray lines and read the value here. And this corresponds to a case where if a specific well was not fractured into water, what would be the performance? And now we plot the original normalized performance factor on the left, and then liquids corrected normalized performance factor. which eliminates that saturation and relative permeability part from the consideration and says, okay, we're only looking at permeability itself, drawdown, and fracturing. And for an example, let us take an area where we have multiple operators. Here we see wells, and different colors are different operators. We can see several of them: red, black, white, green, blue, and this brown. If you look at our plot, our main plot, master plot, normalized performance factor versus water-gas ratio, we can consistently see that red points are in the upper portion in the same area. Then black points also are in the upper portion versus brown points are here in the lower portion. And for white points, we can see that they are consistently in the, for every water-gas ratio, they look to be below the average line. Specifically, what's also interesting is this area where we have white operator with a lower performance. We can see that performance color is lighter, means lower performance, and this performance color is darker, higher performance. So lower, higher, lower, white, black, white. That was a very interesting area to look at, and let us look in the detail in this area. Here is a cross-section. We have 4 wells, 1 well here, 1 well here, 1 well here, and 1 well here. And here we see just some logs. I don't put here log interpretation, but just logs themselves. And I used Dynamics software to do that. That was really helpful. And what we can see is we do see some lower resistivity in the upper portion. And specifically, we can see lower resistivity in this area here, even lower, and also higher density. That suggests higher bulk volume of water. Then lower porosity means higher saturation. So most likely here is in the upper portion in this area, there is a higher water saturation. But we can see that black wells are also here. White wells are near, but black wells are also here. Looking at our master plot, gas normalized performance factor versus water-gas ratio, we can see that black points, though, don't generally get higher water-gas ratio, and they are above this green line, above the average. And white points, they have lower and higher water-gas ratio, but they are below the average line. On the performance factor versus propant mass, we can see that some white points have high propant mass, but not that high performance. And looking at that plot, we can see that the highest water-gas ratio with white points, these wells were completed in the upper portion, somewhere in here, with higher saturation. Also interesting to look at water-based performance, not gas-based performance, but water-based performance versus depth. And again, we see that even for water, normalized performance factor is lower for white operator than for black operator. From all this, we can conclude a couple of things. First, high water-gas ratio with certain wells are because of the completion where they were completed, but also for every propant mass, even water performance is lower for white operator, which suggests that black operator does more efficiently or did more efficiently more efficient fracturing here in this area. Another example in the same area, now we are looking at red, blue, and green operators, and here is a cross section. Again, we can see in the upper portion, the lower resistivity, and again, lower resistivity here in the eastern part. But we don't see a drastic difference between the wells. And but we see that on the gas normalized performance factor versus water gas ratio, we see higher performance with red wells than with blue and the green. Also, looking at the propant mass, we see that for specific higher propant size, we see the same performance. And water gas ratio we can see was consistently lower with the red wells than with the green wells. And here, sorry, I cannot see it very well because the zoom screen just overlays. Let me see if I can. Yes, yeah, now I can see it. So here, what we can see on this plot is for every given depth, water-related normalized performance factor is higher with blue wells and green wells. What's also interesting is that in this specific case, there is a transition or apparent transition from gas to like gas saturation to oil. Here, these operators, green and blue, they report more oil, which we can see from this plot. Oil gas ratio or condensate gas ratio is highest with the green wells. And this explains why gas performance is lower in this specific case. In addition to additional water here, which was caused by probably completing in this area, there is also effect of, we are not talking about gas, we are talking about oil in this case, specifically here, which has to be taken into account as well. So several major conclusions. These wells completed near the top here with a higher water saturation, that they have more water, but also we are talking about bigger jobs, and also we're talking about the oil versus gas here. And finally, let us look at all the operators, all the 10 operators here, where we look at only dry gas wells versus wells with gas and liquid. So for every operator, we have performance for dry gas wells and wells which have hydrocarbon liquids as well. And for a Vintive, for example, we see that dry gas wells, the gas performance is higher. For wells with hydrocarbon liquids, the gas performance is lower, but this potential oil component compensates for the gas. So when comparing dry gas to hydrocarbon liquids, we can see that there is this compensation. Shale wells performance factor overall is relatively high, and all wells, according to production data, are dry wells. Operator A, we can see dry gas wells and all wells, gas performance is the same. So this additional, and here I noted as equivalent oil performance up to, it can be, it's simply taken from the water cut. So this is probably a gas that is, this is probably hydrocarbon liquids which are condensate. This is not oil in the reservoir. Then we go from left to right overall on decreasing performance. And we can see from operator to operator the change. For example, operator I, we see that again, dry gas wells and all wells, they have the same performance, which is lower than the performance of these operators in the left. And we can note the operator D, which has a lot of liquids, but even dry gas wells or wells that are dry gas in the production data, they are low. So we do definitely see change or differences in performance. To conclude this presentation, the main takeaway is that water strongly affects performance, but completion and operation practices matter. Public data within BC Montney is extensive. It is high quality, a lot of files, a lot of types of the files, and it is helpful to quantify well performance and to apply some physics in the analysis. Water does strongly affect performance, but calculating equivalent dry gas performance may be useful. Completion and operation practices vary by operator and they are important. And then possible actions to improve performance or to prevent lower performance is to avoid completing fracturing into zones with a higher water saturation. And then when we land the well and design our frac jobs, we want to maximize hydrocarbon fracture area for a given proppant mass, as an opposite to the example that we saw a couple of slides ago with the black and white operator, where for a given proppant mass, white operator got lower performance even in terms of the water. Then managing flow and bottom hole pressure should help, like adjusting tubing diameters or installing velocity strings artificial lift. And within certain operators in the area, including Ovintiv, oil production is a significant performance component. So when we're looking at the gas-based performance, let's not forget about oil. And we always need to remember that public data may have limitations, including availability of pressures and reporting. With that, I'd like to thank you for attention. And here is some useful reading. And these papers were helpful in this study and inspiring. Please take a look at them if you have time. Also, the questions can be sent to my email address later. Thank you very much.
Thanks a lot, Viacheslav, for a great presentation. We're still waiting for questions from the audience, and I'd like to remind everybody that you can ask them in the chat window. We've got about 30 minutes before the end of this webinar. And while we're waiting for the questions, I know that some of the questions have been sent before the meeting to your and Boris' email. So I would leave to Boris to bring those questions, on the table to start the discussion. But before that, I would like to ask for a little favor from the audience. So I'm going to launch a poll. It's not the survey that I mentioned at the very beginning of this call. It's just a poll, to understand us better, the demographics of the call today. So if you don't mind, please answer those 6 questions. They are really short. They won't take more than 1-2 minutes to answer, and that would allow us to understand whom do we have here, whether we have more student members or professional members or people that are not yet maybe SP members at all, and whether this is the first event, how have you heard about this event. So if you can please respond to those poll that I just launched by answering, that would be greatly appreciated. And meanwhile, while you are responding, Boris, I'm passing back the floor to you to start the Q&A session, please. So the poll will be open until the end of the call. Please reply to your convenience. So thanks. We've got already 3 people out of 12 participating. So I would encourage everybody to respond. Thank you. Boris, Viacheslav, back to you.
Yes, thank you, Konstantin. So the first question was regarding how to take into account the geology, because you showed that there is a factor which is impacted by the operator's efficiency, but there is another one which is like permeability, porosity, fluid properties, and so on. So how do you think we can take into account all this to really see the impact of the operator's efficiency?
Thank you for your question, Boris. Yes, this can be taken into account even using public data. Permeability is an important parameter it does affect, and we can determine permeability using additional data like DFIT data, for example, or flowback data. Flowback DFIT analysis is widely used here in North America. And another layer of complexity, just we take that data, analyze, maybe do similar maps, and try to distinguish between the permeability part and the operational part.
But do you think it's something useful? You are going to try to do it, or what you showed like on the same area, that more or less we can assume that permeability is the same, fluid properties are the same. So do you think it's worth doing it or not really?
I think it is. I think it is worth doing that. At least it's very interesting to try to do it, and maybe I will incorporate it and in the next analysis I will just see maybe just for some of the smaller area to see whether it affects and how.
Okay. So do you have other questions from the audience?
There's one question in the chat, Boris, if you can look there. I think it came from Rodrigo.
Could you read it, please? I don't see
Yeah,
the
sure.
chat.
Rodrigo is asking, congrats and thanks, Viacheslav, for the presentation. What lessons learned from your work do you think could be applicable in other unconventional plays, such as in the USA or Argentina?
Thank you for your question, Rodrigo. I think that first starting with how wells operate. When I started to look at the data and started the analysis, I did not know specific data patterns, what they mean from the performance point of view, from operational point of view. But after I consulted these completion files, I kind of understand what causes what. And this is a good lesson, I believe, can be applied anywhere for any unconventional well. You look at how rate behaves versus or reciprocal rate versus square root time, and you see certain patterns. These patterns indicate something. Regarding the water, it probably depends on geology, but I would also look at that if performance is correlated with water or not. And if yes, that's maybe a similar situation, but I don't really know much about the geology of other places.
Thanks, Viacheslav. I will probably, abuse a bit and use my role of the host today. I'm just curious, what kind of digital tools did you use for all these plotting that you've done? Because I believe you probably use some mapping applications to map, some regional data. You've done a lot of plotting. So was it something commercial or self-made, whether it was like an open source product that others can benefit from? If you could just say a few words about that.
For the analysis itself, I used Excel. Then for plotting, I used Surfer, which is a really, really nice and cheap tool. It's really powerful and light. I always do my mapping in Surfer. Then for analysis, for log analysis, I used Dynamics. And this is, again, if you compare to all expensive and hard and bulk softwares, that tool was really easy to work with because I'm an engineer, I'm not even a petrophysicist, but for me it was easy to load the data. Automatically the aliases were attributed and the curves were plotted and the analysis was really quick. So I would say that these three tools were the main ones. And for visualization, we can use any visualization softwares. But maybe later there will be a plan to transfer all this information to some web-based software, but that's just a plan for now.
Sure. Thank you. Thank you. That's really interesting. We've got a question coming from Maria in chat. She's saying, Viacheslav, excellent presentation. Analyzing over 5,000 wells is truly impressive. Are there any insights or recommendations regarding optimal fracture or well spacing based on this work?
Thank you very much, Maria. This is the work going forward. It's the next layer of complexity. This work I performed is more like a screening work, where to look. And then we look at specific area, go again into the completion files. And as a next layer of complexity, we try to understand what specifically caused this. Like, for example, we are talking about not only the proppant mass, but proppant mass, even not per stage. We're talking about we should be talking about proppant mass per cluster. And this is something that was discussed in the Saga Wisdom conference I attended a couple of weeks ago. There was a presentation about public data, and what matters really is proppant mass per cluster. And again, DFIT data, and all the data is a lot. Just we need sufficient time to devote to analyze this data and specific purpose to do a specific area.
Thank you. There's another question coming from Maria. Have you seen any wells on a boundary dominated flow, Viacheslav?
I have seen a lot of wells on apparent boundary dominated flow, like I showed in my example. You see a -1 slope, but in most cases it was not a boundary dominated flow. And not having the pressure, we cannot truly say that whether we see it or not. But according to the time when these inflections occurred, that probably was too early. So probably the short answer is no.
Thanks, Viacheslav. Boris, have you got any questions that came through email? I think we have time for the very last question. So if you can just pick up and bring something for Viacheslav.
No, I think we covered more or
Okay.
less
Okay.
all the questions which you sent before. We covered during the discussion already.
Lovely, lovely. Well, with that, Viacheslav, thank you very much for an amazing presentation. I really found it very, inspiring, and learned a lot myself, being a production engineer. Boris has done a fantastic job being the host, moderator today, and I hope he'll join later, for other events. With that, I would like to thank everybody joining the call today. So once again, those of you who would respond to the survey, that will be automatically sent after the end of this event would receive the slides of Viacheslav's presentation. And then we're looking forward to see you on other virtual, hybrid, and in-person events in France, whether it's Parisian region or in the south of France. You are always welcome to join us. Thank you very much.
Thank you very much, Konstantin, and thank you, SPE France, for organizing this event and for all the attendees.
Perfect. Thanks, everybody. Have a great afternoon. Cheers. Take care.
Thank you. Bye-bye.